Photoelectric effect. The phenomenon of photoelectric effect was first observed by Heinrich Hertz in 1887. He was studying the electromagnetic waves. In between his experiments with electromagnetic waves, he observed a special phenomenon happening in the experimental setup. The experimental setup consisted of two large square metal plates A and B connected to source of high voltage. The plates are connected through thick copper wires to two polished brass knobs K1 and K2. The voltage is high enough such that the air gap in between the knobs K1 and K2 gets ionized and provides a path for discharge of the plates. These two plates form a condenser of low capacity. When the potential difference between the plates is very high, the air gap between the plates becomes conducting. Consequently, condenser discharges producing electromagnetic waves. That was his original experiment. The electromagnetic waves were detected by using an unclosed metallic ring having small metallic spheres C and D with some gap. It was held in a position such that the electromagnetic field produced by the oscillating current is perpendicular to the plane of the ring. The oscillating magnetic field linked with the ring produces large induced EMF which causes a spark to appear across the spheres C and D. That was the original experiment done by Heinrich Hertz in order to detect electromagnetic waves. While doing this experiment, Hertz noticed that the sparks in between the knobs K1 and K2 occurred more steadily when ultraviolet light was directed at one of the metal poles. When ultraviolet light was incident on the metal knob K1 or K2, the discharge, the spark in between K1 and K2 becomes more steady, which means that this incidence of ultraviolet radiation on the metal knob makes the spark more steady, makes the discharge of electrons more steady. So it indicates that the incidence of electromagnetic waves on the metal knob induces or produces some more emission of discharged electrons. Hertz could not pursue his observation, but his student Philip Lenard studied the observation in detail and observed that the cause of the spark was electrons emitted when the frequency of electromagnetic wave was sufficiently high. This phenomenon is known as photoelectric effect. Photoelectric effect is the phenomenon of emission of electrons from metal surfaces when light of radiation of suitable frequency falls on them. The emitted electrons are known as photoelectrons, and the current so produced is called photoelectric current. Different metals emit photoelectrons when they are exposed to radiations of suitable frequencies or wavelengths. For example, alkali metals like lithium, sodium, potassium, cesium, etc. shows this phenomenon, this emission of photoelectrons with visible light, whereas the metals like zinc, cadmium, magnesium, etc. produces photoelectric effect only when irradiated by ultraviolet light. That is, these metals require a radiation with more frequency. Philip Lenard failed to explain this phenomenon of photoelectric effect. A few years later, in 1905, Albert Einstein realized that this photoelectric effect could be understood if the energy of radiation is concentrated in small packets called photons. Photon means light quantum. The term photon was coined by a chemist, Gilbert Lewis, in 1926. With this idea, Einstein explained the photoelectric effect. He explained the photoelectric effect on the basis of quantum theory of radiation. For this, Einstein was awarded Nobel Prize. This is the experimental study of photoelectric effect. Experimental study of photoelectric effect. This is the experimental setup. The experimental study was carried out by Philip Lenard. His experimental setup consisted of an evacuated quartz tube, T dash, which is provided with two electrodes, emitter and collector. The electrode emitter E is made of some photosensitive metal. Light is incident on the emitter electrode through the window doubling. A potential difference is applied across the emitter and collector with the help of a potential divider. This enables to apply variable potential difference between emitter and collector. The photoelectrons emitted from the emitter are collected by the collector electrode. The photoelectric current in the circuit is measured by an ammeter. With this arrangement, we can study the effects of different factors that affect photoelectric emission. Then what are the factors which affect the photoelectric emission? There are four factors which affect the photoelectric emission. First one is intensity of incident radiation. Second one is the potential difference between emitter and collector. Third factor is the frequency of incident radiation. And the fourth factor is the nature of photosensitive metal. Let us examine the effect of these different factors on photoelectric emission in detail. First of all, we can consider the effect of intensity of radiation. Effect of intensity of incident radiation. For this, all other factors are kept constant. When we study the effect of intensity, frequency is maintained constant. Potential between emitter and collector is maintained constant, and we use a constant, we use a particular photosensitive metal. So in order to study the effect of intensity, we maintain all other factors constant. So maintain the collector at a definite positive potential with respect to emitter by adjusting the potential divider using incident radiations of different intensity and having a fixed frequency. We use incident radiations of fixed frequency. And we maintain a constant potential between emitter and collector. And photoelectric current is measured for different intensities of radiation. Photoelectric current is measured for different intensities of radiation. And the graph is plotted by taking intensity on x-axis and photoelectric current on y-axis. Then we can see that the photoelectric current increases linearly. The photoelectric current increases linearly. Photoelectric current increases linearly with increasing intensity of radiation. It means that the number of photoelectrons emitted from the sensitive plate is directly proportional to the intensity of incident radiation. If the light has more intensity, more number of photoelectrons will be emitted. Effect of potential between emitter and collector. When we study the effect of potential, we maintain the frequency of radiation and intensity of radiation as a constant. If the frequency and intensity of radiation are kept fixed, it is found that we change the potential between emitter and collector, and we measure the photoelectric current for different potential values, and a graph is plotted by taking photoelectric current on y-axis and the potential along x-axis. Then it is found that the photoelectric current increases gradually when we increase the potential, until a stage becomes where the photoelectric current reaches a maximum value at a particular positive potential. The photoelectric effect gradually increases with increase in potential and reaches a maximum value at a particular positive potential. When the potential is increased further, there is no increase in potential photoelectric current. The photoelectric current has a constant value. Photoelectric current has a fixed value after the photoelectric current has a fixed value when the potential, positive potential, is further increased beyond the particular value at which the photoelectric current has a maximum. When the photoelectric current reaches the maximum value at a particular positive potential, the photoelectric current attains saturation. which means all electrons emitted from emitter reaches the collector. There will be no increase further, even though we increase the positive potential. The current attains saturation. Suppose if we apply a negative potential to the collector with respect to emitter, what happens? If we apply a negative potential, this is. If we apply a negative potential for the collector with respect to emitter, the photoelectric current rapidly decreases. Photoelectric current rapidly decreases and it becomes zero at a particular value of negative potential. At a particular value of negative potential at the collector with respect to emitter, the photoelectric current reduces to zero. And this minimum negative potential given to the collector at which the photoelectric current becomes zero is known as the stopping potential or cutoff potential V0. The stopping potential or cutoff potential is the minimum negative potential given to the collector at which the photoelectric current becomes zero. Suppose the experiment is repeated. The experiment is repeated with radiation of same frequency but having a higher intensity. Then the curve will be like this. This is done for a particular intensity and this is done for another intensity which is greater than the first case. So what is the difference? The saturation current is greater for a greater intensity. The saturation current is greater. This is the saturation current. Saturation current is greater. In this case, it is a smaller value. So the saturation current is greater for a greater intensity, but the stopping potential is the same. The stopping potential is the same. Even though intensity is increased, the stopping potential is the same. This means that for a given frequency, we have kept frequency constant. Frequency is kept constant. Frequency is kept constant. For a given frequency of incident radiation, the stopping potential is independent of intensity. For two different intensities, we got the same value for stopping potential. Therefore, the stopping potential is independent of intensity for a given frequency. The stopping potential is independent of intensity. For a given frequency of radiation, suppose the stopping potential is V0, then what is meant by the stopping potential? Stopping potential is the potential at which the electrostatic repulsive potential energy of the collector can stop all the photoelectrons emitted. It can stop this electrostatic repulsive potential energy from the collector balances the kinetic energy of photoelectrons. So the stopping potential is a measure of the maximum kinetic energy of photoelectrons emitted. It is a measure of maximum kinetic energy of the photoelectrons emitted. And it is the maximum kinetic energy of photoelectrons that is just stopped from reaching the collector plate. If m is the mass of the photoelectrons and Vmax is the maximum velocity of photoelectrons emitted, then the maximum kinetic energy of photoelectrons will be half m Vmax square. If E is the charge of each electron and V0 is the stopping potential, then the electrostatic repulsive potential energy or retarding potential energy will be equal to E into V0, E times the stopping potential. Then we can write the stopping potential is a measure of maximum kinetic energy, or the maximum kinetic energy is balanced by the retarding potential energy. Therefore, we can write half m Vmax square will be equal to E V0. Half m Vmax square equal to E V0. Now let us consider the effect of frequency of radiation. In order to study the effect of frequency on photoelectric emission, we maintain the intensity of radiation and stopping potential at a constant value. And we take radiations of different frequencies but of same intensity. For each radiation, we study the variation of photoelectric current and the potential of plate C, the collector plate. We take different frequency radiations, and for each radiation, we measure the photoelectric current under different values of collector potential, and we will find out the stopping potential. For each frequency of incident radiation, we will find out the stopping potential. And the graph is plotted taking frequency on x-axis and the stopping potential on y-axis. We can see that the saturation current is same for different frequency radiations. Saturation current is same because it depends on intensity, and we have fixed the intensity in this case. For the saturation current will be the same, but the value of stopping potential is different for different incident frequency radiations. Greater is the frequency of incident radiation, the higher will be the stopping potential. Because greater the frequency of incident radiation, the photoelectrons emitted will have higher potential energy. So more stopping potential is needed to stop them. And moreover, we found that there is a minimum frequency nu zero. There is a minimum frequency nu zero, which is known as threshold frequency. Threshold frequency of incident radiation. And this is the frequency at which the photoelectric emission begins. For a frequency less than threshold frequency, there will be no emission. If nu zero is the threshold frequency, H nu zero, that is the energy of incident photon having threshold frequency, is the minimum energy required for photoelectric emission. So there is a minimum frequency required for photoelectric emission, that is known as threshold frequency. And at the threshold frequency, the stopping potential is zero. It means that for threshold frequency of incident radiation, the emission of photoelectrons is just possible. Electrons are just ejected, but they have no kinetic energy. For incident radiations of frequency less than threshold frequency, no emission of photoelectrons is possible. These are the experimental observations regarding photoelectric effect. From these experimental observations, we can conclude 4 points. They are known as laws of photoelectric effect or laws of photoelectric emission. First one, for a given frequency and for a given metal and frequency of radiation, for a given metal and a given frequency of radiation, the number of photoelectrons emitted is directly proportional to the intensity of incident radiation. Second one, for a given metal, there exists a minimum frequency of incident radiation below which there is no emission of photoelectrons. This frequency is called threshold frequency. Third law is, above the threshold frequency, the maximum kinetic energy of emitted photoelectrons is independent of intensity, but depends only on the frequency of incident light. In other words, the stopping potential is independent of intensity of incident radiation, but the stopping potential depends only upon the frequency of incident radiation. And moreover, the saturation current depends on the intensity. But stopping potential or the maximum kinetic energy of photoelectrons emitted depends only on the frequency of incident radiation and is independent of the intensity of incident radiation. The fourth law is, the photoelectric emission is an instantaneous process. The time lag between incidence of radiation and the emission of photoelectrons is very small. It is less than even 10 raised to minus 9 seconds. Less than 10 raised to minus 9 seconds. So the photoelectric emission is an instantaneous process. These are the laws of photoelectric emission. Thank you.